Yes? All of you?
Second, yeah.
Second, right? Distinguished. Good. What we mean by latent space in Gen AI models? Right, so this, we saw that a couple of people had it wrong, which makes sense because we never actually went through the formal definition of the latent space, what it means. So remember, in autoencoders that Gerta explained briefly, and GANs and other machine learning models like principal component analysis, what we are trying to do is to start with the data. Okay, so we come up initially with a set of initial features, what we say, and then there are some type of mechanisms, some type of functions that take these initial features and come up with a different representation for those features. Okay, in principal component analysis, for instance, what we are trying to come up with is with a compressed representation of the initial features. So, for instance, if you have 728 initial features, you would like to identify what are the most less correlated features that most of the information of your data is highlighted. Okay? So in principal component analysis, for instance, we call it the principal components. You are extracting axes that, if you project the data onto those two axes, they maintain most of the variance. The data maintain most of the variance. Okay? Now, the set of those axes, we call them latent space. It's a space spanned by different patterns of the data. And most likely, they are useful. That's why, for example, in PCA, they highlight data, the variance of the data, they maintain most of the variance of the data, they maintain most of the information about the data, the useful information.
But reduced
Now,
the dimensionality.
Exactly, and it reduces the dimensionality. Now, in an encoder-decoder, that is actually at the heart of it. The latent space is at the heart of this type of architecture. You start with your original data, and the goal is actually you would like to construct a neural network where at each layer you are reducing the number of neurons.
Zipping.
Compressing.
Compressing.
Right? And now the set of neurons at the very last layer of an autoencoder, of the first part of this special architecture, is called the latent space. The neurons, by themselves, they define the latent space. Okay? It's a low-dimensional space where your data can be actually visualized. Good? If you try to visualize, you won't see back in real images, but you see a set of patterns that are very useful in order to understand your original images. Okay? So this is actually the latent space, and that's why we say it's a compressed internal representation of data features or patterns. Okay? Any questions? No. Which architecture is most associated with gradual denoising during image generation? And again, we didn't know through officially to that, but when you see denoising, means diffusion. Okay? So you are getting rid of the noise and you generate something new after you have removed the noise. That's what Gerta showed in one of her slides. What is the key learning of LLMs? Right? Gerta mentioned that you have a set of tokens. The task will be to actually come up with an X token that has the highest probability. AI transforms. AI helps. AI forgets. Sleeps. So the highest probability could be, for example, transforms. And that's what an LLM will output for you. Good? Why is GAN training often described as a min-max game? Exactly. So it's a dual game, right? Cost function, loss function, min, max. We are minimizing, maximizing at the same time. There are two networks. One is maximizing, the other is trying to minimize in order to come up with the best set of underlying parameters for both networks at the same time. Why can a GAN fail if the discriminator becomes too strong too early in training? Too weak to improve. Vanishing problem, right? We said that information can be lost while training. And therefore, the generator may receive those gradients that are almost zero. So the back propagation that is happening will actually transmit zeros. And I think last one, which statement best distinguishes generative models from discriminative? And that's exactly the definition, by the way. So the discriminative models, they are trying to come up with a boundary. They are trying to distinguish between the two classes, right? For example, can we say, is it safe to say that support vector machines are discriminated? You know, remember what support vector machines are? These are the models that come up with a straight line and then two boundaries, margins, and using this decision boundary, we are able to actually now categorize data based on their labels. Yes? Gen models learn the underlying distribution. That's by definition. For example, the autoencoders, we said latent space. Even if we come up with a low-dimensional representation of your data, which is called the latent space, what we do, in other words, is actually we are learning the distribution of that space. Good? In variational autoencoders that you're going to see in the lab, what we are actually taking into account and make use of is that the distribution itself. It's something called, in statistics, called Bayesian statistics. Okay? So rather than, the idea is that rather than learning the parameters of an underlying distribution using data, what we are trying is that we are learning the distribution and then we are sampling from this distribution and generate points. Okay? That's what actually Bayesian, one of the usages of Bayesian statistics does. Good? Okay. Any questions on the quiz? No? No. What we're gonna do is we will let you today, you are advanced, right? So 3 days, 4 days, you know what to do. So you can start this lab by yourself and load the data, which is the fashion of NIST, and then start seeing something there. And then we can discuss it together, but I want you first to just, try this out, look at it, see what it is. Try to connect it with what we discussed in the theory. Okay, and then we can discuss it together. Huh?
So run it cell by cell and check the output that you get and lead it to the code what is doing and so on. And after it will go to the discussions and to lead you to leave this session now because we are
starting with this one.
The introduction, you can do it code. It's not so important. This one is actually the important one. So this is what we want to discuss today. The fashion and NIST, image recognition and generation. Reconstruction, sorry, not recognition. We're not doing recognition, by the way. Most of the lines in the code you already know from the last time.
Don't run all at once, let's say. Do it step by step in order, as I was mentioned, to understand what the code is doing and what the output you get at each stage, like we have been doing. Yesterday.
Feel free to use Claude, ChatGPT, anything that you like today to get knowledge. I mean, you do not have to produce any code because the code is given, but if, let's say, you have a question about a particular line of code, use ChatGPT to get the reason, and then discuss it with yourself. If this is a good reason, I think it will be good. Okay, ChatGPT is intelligent.
You are saying better than us.
Yeah, it's much better than me.
Po, mbaroj. Ja ke këtu jeshile, jo, po thot këtu jeshile, do të thotë që ka përfunduar. Tani kalo tek këtu tani ti ke instaluar transformers. Nuk ka output ose është vetëm instalim. Tani në këtë moment i po importon sa librari që të duhen ti përdorësh. Okej? Nuk na duhet. S'po importojmë se s'na duhet. Kupton? Na duhen transformers, nga transformers na duhet pipeline se do ndërtojmë. Po importojmë torchin dhe pandas për të krijuar ato datasetin tonë, okay?
Pandas është vjetat neurale?
Jo, pandas është për të përpunuar dhe për të krijuar ato matricat me dhënat që kemi ne. Okay?
Po torçi çfarë është?
Për vjetat neurale, po të shohim po të përdorë. Transformer për të procesuar tani.
Këto janë si thua të varura në kërras dhe tensor.
Kjo është këtë po duash mos është merr që GPU-ja s'të duhet, okay? Small changes in prompt can significantly make the outcome. And prompt is artificial intelligence maximum benefit të fjallis. Se të shëtë ka outputit, s'ka një të outputit, s'ka një dhe
Outputi është këtu, edhe poshtë.
With be a thing. Shaputi që ka gjeneruar të
Press a button and it's going to explode the whole block.
It was like a decoration.
My dad was saying what was going to get
Nuk po punon me këtë. Ti nuk po punon me këtë që po punon me zotin. Ti nuk po punon me këtë. Se janë dy. Ti e kemi një dataset tjetër. Kjo është interdashë, kjo është mirë. Që ka të skip të punon me këtë, kemi dhëna që shkoj. Lodhim e mëshë, me këtë trade testing. Kjo është thjesht për të gjeneruar, por nuk është për gjeneruar më tani. Ne pra për të shumë për të gjeneruar. Tani prompt këtu është deep learning, është feature share, këtu prompt tani po vjen different prompts. Për të gjeneruar se çfarë se ose ishin
Yeah, that's what they offer.
But it doesn't work.
Yeah, because you used yesterday, right?
të që printojnë.
But I think it's around
Mimi io in ekzekutuara
even if you have CPU, that will produce an empty set.
Edhe kjo ka plotësuar me ka Generative. Ka konceptu tani. In the year 2050, shiko si ka tani. In the year 2050 ka gjeneruar dhe i ka autofinanse ka Olimpikës. Kjo është ajo që për prontë. Kjo është. Okej, s'pëtan në poshtë. Un sentiment analysis. This was fantastic inspiring. The purchase pipeline center. Io su cosa Tokenizer është standard. Teksti është lartë në rritmo, do të ndaj një kohë, do të ndaj një fjallë. Se tokenization është të tu tani bën tekst summarization është një vërë. Ka këtë teksti tu e do tani një përmbajtje, summarizero indeksi pa që vjen për qita. Okej, po, këtë të shumë po të këtu. Jo këtë, s'po punojmë këtë.
është një lartë po generative artificial.
Kjo është introduction, mund ta testoni edhe vetë, se janë dy.
There is no why. Why is that? So there is no, I mean, you should put two arguments there, right? X and Y. Traditionally we do X and Y. But we do when we have a classification for regression supervisor. Right now we don't have a supervisor. It not really needs a label. So because the code needs to receive two parameters, then that's why I just give it back to X. So this is basically the idea of the OSI code. So it receives the input data, creates a low-dimensional space of the data, sees this as an input, and reconstructs your original data back. And your cost function is actually how far the original from the reconstructed data are. Good? Makes sense? Yes, sir. As many? Ah. Yeah, you can do the... I think it's a syntax. Can you change it to 0?
Dobra, to GPU available. Jak zero GPU, to runtime, це було. I'm changing
Dimension functionality. No, actually, what it actually basically tells you is that you are, I mean, this is like a Python syntax. Yeah, it's actually for the counting. So if you do -1, you don't really have to specify the number of training data. So they have coded -1 there just for convenience. Great, I like that you are putting the little details. It's important. Yes. Yes. And some of the code may get stuck. Simply because of that. Remember I said things are changing all over anytime with tensor, especially with TensorFlow. So yes, and in some months probably you may use this notebook and you may see another error. But LLMs are here to help for that reason. Okay? LLMs also are integrated now in Google Colab. So it's not just ChatGPT, Gemini who can give you a solution for that. So there is a button for many people I've seen, fix the problem. So you click on it and it gives you on the right path that tells you how to fix it. Right? Okay, so what we do in this lab, we're gonna run two different architectures for generating images. Okay? And for demonstration purposes, we are using one particular dataset. This is called the Fashion MNIST dataset. You have probably seen it before. It's the same as the MNIST dataset with the handwritten digits, but now instead of handwritten digits, you have type of clothes, like shoes, t-shirts, shirts, dresses, and so on. Okay? So when you load the data, which is actually preloaded in Keras, and you load it, you can actually discover the different types of labels that you have. Each image is still a 28 by 28 image, but it shows something different. And the labels are here for us to understand what they are about. So you have t-shirts, you have pants, you have pullovers, you have a dress, you have a coat, total of 10 classes. Okay? And what we're going to try to do is produce images that look very similar to those training data points. Make sense? Any questions here? No, right? Now, these are like a couple of samples that we are extracting from the data set just to see how they look like. So you see a shoe, a t-shirt top, a dress, a pullover, a sneaker, and so on. Okay? Now, first thing that we do is like the regular thing that we always do. We know that we need to pre-process the data, so that's why we would like to bring down the 255 to 1, okay? And we divide everything by 255. We had a nice question about why it's -1 in the reshape, which is again syntax, Python related. So the -1 is just simply for you to not remember how many samples you have. It's just you indicate -1 and you get back the number of samples, okay, from Python. So that's all. Nothing special. Yes. So we are just getting out the training shape and the test shape. So we have 784 features. Keep this in mind. You know that already the features are the pixels, right? 784 and 60,000 training observations. Good? Okay, an encoder-decoder framework. That's not a GAN, it's a different architecture. And Ogerta showed what this looks like in one of the slides, but I'm going to show it again one more time just for us to remember. Here we are. This is an encoder and decoder framework. That's what we are going to try to implement here. So what is this about? Remember that we would like to take images, the 784 features, and 60,000 observations, give it to a network which we call encoder, get something that is in the middle which is called the latent space, receive this as an input for the next network which is called the decoder, and get back images. Okay? Is the process clear? So the raw data are actually the 60,000 images that you are getting. Basically, it's like 784 features. That's all the network sees. It doesn't really see whether it's a shoe, whether it's something else. It sees 784 features. And these are actually pixels. Now, what the encoder will do is that it will take the 784 features and come up with a low-dimensional set of features. The low-dimensional set of features means that the 784 will be reduced to 2. So the encoder will be responsible to tell you that you need only 2 features to get a good representation of your data. Okay? And the reason why we are adding a neural network is simply because of that, because the neural network will find a way to identify 2 features or generate 2 features so you get a good representations of your data with only 2 dimensions. That is going to be the latent space. Okay? PCA is doing exactly the same thing, by the way. Principal component analysis is doing what you are seeing here in the encoder phase. It takes data from a high-dimensional space, does a couple of computations, mathematical operations, and gives you back what? 2 principal components. It does it in a different using a different mechanism. Here we are using neural networks for that. Okay?
It is a neural network. This autoencoder is a neural network.
What?
The autoencoder is
an architecture of a neural network. Yep. Now, the job is not done. The PCA stops there. Sorry, let me finish this and then we'll come with your question. The job is not done because the autoencoder doesn't finish there. It takes the latent space, these 2 dimensions, these 2 neurons, as input to the next network. Okay? And the next network now is actually decompressing, so it is adding more layers with higher dimensions than 2. And eventually, at the very last layer, here, you're going to end up having 784 dimensions, the same as the input here. So we go from 784 to 2, from 2 to 784. And now, if all the parameters here are trained properly using backpropagation, the output here, the reconstructed images that you are getting from these 784 features, will be very similar to those. Okay? Do you see what is the loss function here? The loss function, like in the first day, was difference between y and y hat. Here it's going to be difference between the raw data and the reconstructed data. So one pair of shoe with its reconstructed pair of shoe. How similar are they? That's going to be your loss function. This is going to be the underlying loss function that you optimize and you train this network. Good? What's the beauty of it? The beauty is that you have access to that space. And now using the latent space, if the network has been trained properly, this latent space is a very good space to represent your data in 2 dimensions. I mean, it could be 4 dimensions, 5 dimensions. I'm just mentioning 2 as an example, okay? Don't get confused about this. So, I'm getting back to the code now because I think we are good. We have an encoder, decoder, so we need to build two neural networks. One is that takes the 784 and gives you 2, and the other one takes 2 and gives you 784, right? Okay, that's the first part here. And that's all you need. This is how we built our model in TensorFlow. This is the encoder. This is the decoder. In the encoder, you have the following. You have inputs to be 784 pixels, yes, pixels, which are the features. Then you are reducing the dimension, 128. Then you are going to the next layer, 64. And then you are going to the next layer, which is 2. That, if you just run this network, it will output 2 features for you. Good? Now, the decoder part, which was the other part, it receives as input the output from the encoder. So it receives here 2-dimensional representations of your 60,000 training observations. Latent D is equal to 2. We set it up initially. All right? And now the idea is that you should go back to 784. So you see that you start from 2, 64, 128, 784, and along with the activations, by the way, and that is it. There is no probability, there are no probability activation functions anymore because we are not doing classification. We're going to do reconstruction here. Okay, and that's all you need. You need 784 as input, 784 as output. And in between, low-dimensional spaces, which are 2. Now, how do you join these two together? You see here that these are 2 pieces of code that need to get together. In Keras, within Keras, you just simply join them. That's all. The encoder and the decoder, and you give a name to autoencoder, and that is it. All right? Let's see something now, which is the next step. Compiling is the next step. Like with all the models that you have seen so far, you need to compile using an optimizer and a loss. I'm missing something. What is that? Metrics, very good. So remember that we need to monitor the performance, right? So all times we used to do classification, so we had accuracy for that. Do we have now any similar type of metric? No. That's not a classification task anymore. This is a reconstruction task.
Just to interrupt you because she made a question.
Okay.
Because why we are using the same data set. So it's train out or it's train out again. Reconstruction. So there is no training and testing and so on because it was in the question.
Yeah, I received the same question too. Very good. So I like that everybody is going through fine details, which is important. So you see how Gerta mentioned, and many of you realize that when we compile and then we go to fit, you see here that I use X-train auto, right? Traditionally, I was using Y-train there, because Y are the classes. Now I don't have classes anymore. I have the I want the reconstructed data. So input is the original input and output is the reconstructed data. And that's what it's going to compare. These two guys will be compared with each other. But again, the first line is the real, the original, and the second one, even if it has the same name, it's going to be the reconstructed one. And they're going to just compare with each other. All right? The rest is history, and you all remember what it is, right? Now we train. We get some numbers there which they look okay to me because we are reducing the loss. And I'm also plotting those curves just to see whether there is an overfitting, right? Whatever old times we have done, we redo it, just with a loss now instead of the accuracy. We don't have accuracy. Now, what I want is a visual actual inspection. Remember we said we are reconstructing data. We are outputting real, data points, images. So I want to actually see what I have done, what the machine has done. And on the top, you see the original images, and on the bottom, you see what are the reconstructed images. You see that they are a little blurry, noisy, but that is something expected, right? Because remember, the original data went through a whole process, like from input to compression and decompression. So you would imagine that, again, what you're going to reconstruct back won't be as close as the original one, won't be so perfect. And you don't want it to be perfect, by the way. You want it to be slightly different. So, I have a quick question and then we go to the next one. What is the difference between this and the generation of data points that we have seen today? Can you claim that these are generated data?
They didn't result from a noise generator.
Very good. So this is not generated data. We do not generate any data. We just reconstruct the original data from a compression, using a compression and a decompression state. So that's why you see there is a one-to-one correspondence between the pair of shoes, the pullover, and the pants. There is a one-to-one correspondence with its noisy version. In a traditional Gen AI problem, what you will receive there is another row with different type of clothes, not one-to-one correspondence. Okay?
The same data set. That correspond.
But there is something also nice about what we have seen so far, about the autoencoder. Visualizing the two-dimensional space. That's always the case when you are working with real problems. You want to visualize and see whether or not there is some structure of your data in a lower dimensional space. Autoencoders are ideal for this because they give you access to the latent space for free. While they are trained, you can always go and access the latent space, which is two-dimensional. What does this mean? The 784 vector arrays are now two. There are only two numbers. Okay? Can I do something with just two numbers? Yes. I can take an x-axis and I can take a y-axis. Take the first vector, which is two numbers, point it, get something. There, one of those dots is what I'm describing, and do that for all the 60,000 training samples. Now, you know the labels also in that case, in this application. You know that some dots are t-shirts, some dots are pants, some dots are shoes. Now, what you do, in addition, is that you are coloring each of those dots based on the label that you have. And you see a very nice structure of your data in a two-dimensional space. Not perfect, but you see something cool. You see that when we are talking about shoes, there is a cluster on the top left that is about shoes. It doesn't do a perfect job when it is sandals versus high heels and stuff like this, but still we cluster, or we see a cluster about shoes. Same thing for, let's say, the pants. The pants, which could be the orange, and some of them, which are the red, are clustered together. Okay? Now, what's nice about this? The nice thing about that is when you want to transmit information, you don't really need the whole network. You just need this latent space. Okay? And I can give you a particular example of a semi-supervised task. For example, a big organization like Meta AI has a lot of images of ourselves with tags. We are actually giving the tags to them because they ask you, can you give me a tag? You say, yes, of course. That's Joyce, that's Ogerta, that's Luigi, that's blah, blah. Okay? They are taking all of this information, and now they can build an autoencoder and come up with this type of low-dimensional space. Okay? So far, so good. They can do clustering if they want and see whether me and Ogerta sit close to each other in this small dimensional space based on features coming from our face, coming from the pictures that they captured. But they can do something even more sophisticated than this. Say that a new picture is coming, taken by Ogerta, and they do not have the tags, the label of it. They can actually do classification. You know how? If they have this space, if they have this space, they know that Ogerta, all of your pictures are located in that region. Okay? So what do? Is that they have the encoder, they take the picture from Ogerta, they give it to the encoder, and the encoder will give a two-dimensional representation of the new picture from Ogerta. And they will project it into that space. And you know, guess what? The point will end up where Ogerta was tagged before.
So classified.
That's classification through a semi-supervised task. Okay? So, that is the nice part. Among others, right? High dimensional data always, like DNA data. We can actually get something like this. So you want to understand the underlying structure of SNPs data, which is 00012. You can actually get something like this by just reducing the dimension. Would you like to explore particular variants of cancer cells? You can actually do something like this and see how they cluster in a two-dimensional space. Good? Okay. Any questions before I move to the next task? I have a question for you. We talked about reconstruction, but today's lecture was about Gen AI. How can we use an autoencoder to generate new data points? Not reconstruct, but generate.
And the relationship will not be one-to-one.
Yes.
We can take around.
Let's, because I think he has the answer.
You can check the output decoding side of that and feed random noise into it.
And then do diffusion.
That's not quite what I thought.
Okay.
Since decoders just do it in a single pass, I think it will generate something between
They will. Actually, you are right, and they will, because what you have in mind is like a mixture between the autoencoder and the GAN. The second network in the encoder-decoder could be actually fed with random noise, and you can generate something. I can guarantee that you won't generate a good data point from that. Simply because that's the architecture of the encoder-decoder is not built like this. But you are correct that you should actually take a random noise and give it somewhere in that network. We will see where. You want to say something?
We can take a random point on the two-dimensional compressed space. So we can take a random two-dimensional point and decompress it, and it should give us.
Good. I think that is close to the real solution. We can take something from the latent space, the two-dimensional space, and give it to the decoder, and the decoder can give us something. Can give us something realistic. it's not quite true what you said, but we are very close to answer this. I can show you what it is. So remember that the encoder-decoder framework looks like this, right? Input, hidden layer 2, something, latent representation space. Output, input, input, output, right? 784, 784. Yes? Okay. Now, within the latent space, there's something very nice that we can extract. We can actually, if you have samples, you can make a safe assumption that the samples follow a particular distribution. All right? And we can make a safe assumption that this distribution is actually a Gaussian distribution. And from the samples, you can even generate two parameters, the mean and the variance. Now, if you have access to the mean and the variance, that's all you need. You can fully characterize something. You can then, using those two parameters, sample from this space characterized by these two parameters, give it to the decoder, and the decoder can give you a new point. That's it. This has a name. It's called variational autoencoder. And this is how people made the autoencoder a variational, which is able now to generate new data points. Alright? Very powerful. Still state of the art in many, many different applications. GANs may outperform in several tasks, but still this outperforms GANs in other tasks. Okay? Don't think that because autoencoders were earlier than GANs, they are not the state of the art anymore. They are still state of the art. Okay? And they all even have a very strong theoretical foundation here, which is the Bayesian statistics, which comes from these mu and sigma that you can actually get from the data and fully characterize a space that you can sample later on. Good? Okay, so that is actually again what I explained in a different picture. So the input is a 2, you have an encoder, you generate the latent space, but then the latent space can actually generate two parameters, the mean and the variance. Then you save this, you reconstruct, you get a 2, but once your network is trained, once your variational autoencoder is trained, you have this mu and z that you can go and sample data from. And you can give to the decoder and generate something. Yeah? Any questions? Now, how to do it, we don't have time to go through, but it's provided to you. And we have all the notes here with what to do, what to follow, okay? This is what it's going to generate, by the way. If I start with random noise, okay, this is the code for generation. If I start with random noise, and I specify my low dimensional space, the coding size, which is 2, by the way, and I give it the mu and the sigma, then the decoder will actually receive the codings as inputs, the random noise, and it will generate 12 images that are very similar to the original ones. Did it do a good job? Not great right now because it's not tuned properly, but it generated. Yes.
Question, because before we had a problem with the function that you have there, so I think it's something that you have, and I just keep the part and I relate it to the random set space, so you create the images, and before it was like creating more noise, it was creating only pixels, and now the function works, it actually creates
Better.
Not as you, but better.
Yeah, no, that's good. Yeah. So you fixed it.
Yeah, but I was questioning if we skip some steps, we will get noise again.
Yes. Because you just start with noise, right? So,
Yeah, so
you will
keep-
receive noise.
You keep the receiving noise until you like improve the noise.
Mm.
The error that you get in the code is only due to the fact
Yeah.
of the appearance version. So version 2 and version 3, let's say that you want to
It's
fix
not about the
something.
name.
Yeah.
Okay. Alright.
I mean, it works and it's okay.
No, it's not because you don't have enough credit. Okay, so we have 1 more minute. And the next part C, we have the guns. Okay? Which you know fully how they look like, the two architectures. We are using the same data set, but give me 1 second to check something real quick. Okay. So there is a generator and a discriminator, right? So we said 2 neural networks for each. So the generator looks like a typical neural network that you have seen so far. Voila. If we just, in part 13, we just show how, what we get out of an untrained generator without going through any training. And input is noise, output is noise, right? Here we are. That is actually the noise that you are getting. But now, after training, this noise will become real images. Okay? The discriminator is again a similar type of network. It receives, again, images. We do different layers with number of neurons and so on. And at the end, we want to output like the probability. Or not the probability. We can output the probability, but here we are outputting whether it's a 0 or 1. Right? That's what the discriminator does. Now, I'm not going to go through this, but it's there for you to go through. We are joining all the different pieces of a GAN using the generative discriminator list. And what we need in order for this to properly run is to actually define the training stage. So you see here there is a phase 1 and phase 2 in that code. Training the discriminator, training the generator. Okay, so the phase 1 and the phase 2 follow exactly the steps from the slides. It's just lines of code that go through the slides. Whatever we discussed in the slides is line by line implemented here. Okay? So remember that there are 2 phases. That one, you are training the discriminator weights, then you go to the other weights, and so on. Good? We run it, and we should stop because the guys from the hackathon are coming. I saw them in here. That's what we're generating through that. Okay? Again, do not run right now anything because it's going to take time, but keep it. Keep those notes, okay? Go through again. Compare the slides with the code and see how they are the same answer. Alright, so enjoy the rest of your day. Whoever is an undergrad and will participate in the hackathon, you stay. Whoever is a grad, we'll see you tomorrow.